We are talking about the drill string design, and in today's lecture, we'll start from this point. As I said earlier also, that when we design the drill string, we have upper part which is composed of drill pipes. Uh, this has to be in tension, and the lower part, that is, we call it the bottom hole assembly, which main component is drill collars. It has to be in compression. Now, compression is provided by the weight of the drill collars, and the tension is provided by the length of the drill pipes. Now, we have to consider the forces acting on this one, okay, and we have to consider the forces acting on this one. Now, based on this tension and compression, we have a chart that drilling engineer always have, and they follow this chart for the drill string, because drill string is the most important component that we have on the rig side, which is very sensitive and vulnerable to break or go through the stresses. Now let's look at the from point A to point B. Now when I say point A and point B, point A and point B represents from this point to this point. Now A and to B is the compression, and their forces are acting downward. Okay, because their forces are acting downward, we are using the minus sign here also. Then tension is the one which we keep it. Then there's a neutral point from B to C. So now B to C is the one where there's no compression and there's no tension. So they are neutral at this point. So this neutral point is the place where drill collar and drill pipes meet. I mean, where there is a joint of drill pipes and drill collars. That is our neutral point we are talking about. Then the above part is the tension line that we are talking about. Okay. First of all, like how we design the drill string, there are some steps. First of all, you have to look at the warehouse, what kind of drill pipes you have available and what kind of drill collars you have available. Then based on that one, you have to prepare this tension load line. These lines you have to prepare based on what you have. So we will see how we can make this line, and you have to definitely include the buoyancy factor, loading line and allowable load line. So we will talk about all of them, how we do that right now after this one. Okay. Let's look at the question first and what it is saying, and then we go for process further. Now, we have to design a drill string. It should be 5-inch. Okay, 5-inch means we are drilling, yes, we are drilling the 5-inch drill string. The weight of drill pipes is 19.5 pound per feet using a new pipe, and the depth we are going to reach is 12,000 feet. So we are drilling a well which is 12,000 feet. We are in reservoir right now. The drill string length is 12,000 feet. We have bottom hole assembly which consists of 20 drill collars, 6 1 by 4 multiplied by 2, 13 by 30. Their weight per feet is 82.6. Now look at the difference between per feet weight of drill pipe and drill collar. Drill pipe is approximately 19.5 pound per feet, and drill collar is 82.6, which is, you can say, 4 times higher than this one. So for design purpose, we have this mud weight, margin of overpull, length of slips, design factors, and so on. Now, the first thing we have to look at it, what is the collapse pressure of the reservoir, of the hole, collapse pressure of the hole. Now, this collapse pressure till 12,000, what is the maximum collapse pressure we can observe? So the formula for finding the collapse pressure is 0.052 multiplied by mud weight multiplied by the length of drill string. This is the formula. Now, because whatever pipes you are going to use, the collapse rating must be higher than this value, which is 6,240. We find out. It is simple. Formula is 0.052. The mud weight, whatever density of mud you are using in the drilling fluid, and later on, what is the total length of the drill string. Okay, so this is the total formula. We find the collapse rating. After you have this collapse rating, 6,240 psi, you look at the warehouse, what kind of pipes you are available, and you check their levels. Now, to know the collapse rating, we have the tables available. For example, let's look at this table. This table is not clean enough, but if you look at the collapse rating of 5-inch pipe, we said that we have a 5-inch pipe, and we are using the 19.5 pound per feet one. So it's collapse rating for the grade G, grade E, grade this one, and grade this one and grade this one. So E, F, and X, and S and G. We have four different grades. We talked about it. So in this one, the collapse rating is 12,001. In fact, the minimum collapse rating for the minimum pipe is 10,000. 10,001 here. Here. So if I put this on the in the paint and I show you it from there. What we are looking at right now, we have a drill pipe which is 5, and what we are looking at its collapse rating. So for the collapse, for the tension, for the torsion, we have the charts and tables. We have lots of tables in drilling engineering because we follow the tables and they have data available. And usually we have the software. Software usually have all those tables already. So we don't really go manually, but as a student, we look at these tables at the moment. So we are dealing with the 5-inch drill pipes, drill string. The drill pipe's weight already is given, which is 19.5. So whatever the grade you are using, for example, we are trying to know the grade E collapse rating. It is 10,000. As you see, it is given here 10,000. Now this rating 10,000 is higher than what we are looking for. Our our reservoir, yes, the collapse, what our collapse rating of the hole we have is 6,240 psi. So which is way quite ahead than the uh, required collapse rating. So that's why grade E drill pipe is feasible for our well. We can easily use it, and its collapse rating is quite fine, 10,001. Now, in order to have a safety factor, you as an engineer, you have to decide what kind of safety regulations you follow. For example, you say that whatever value you get, you multiply by 10%. So you use safety factor as 10% here. Okay. Now, here they are using the design factor, which is 12.5, 12.5%. So we have to multiply this 600 to 250, 6,240 psi with 12.5%. So we multiply 1.125, we get the value 8,899, which is, as you see here, 1.125. We multiplied it. Still, the 8,889 or 8,900 is much less than the 10,000 psi. So it is, we can say that as an engineer, that for the drill pipe we can use the grade E, and its collapse rating is much higher than needed because the whole collapse pressure is 6,240 psi, and our pipe that we have, its collapse rating is 10,000, so we can easily use it. Okay, now you have selected the pipe. You are going to use grade E pipe, uh, 5-inch. Its nominal weight is 19.5 pound per feet. Its collapse rating is 10,000. Okay. Now you know this. You must know. You have to go back again to the table and find out what is the internal diameter of the drill pipe. The external diameter is 5-inch. Then for that you have to go back to the table again here. For example, you are using 9.5 inch. The internal diameter is 4.276. So again, you have to use the tables. And also when you will work, you will see these tables again and again. So probably you will memorize them also. Here it is. Okay. Now you have the ID, internal diameter, which is 4.276, and you have the outside diameter, which is 5-inch. You know that you are going to use the grade E pipe. Any questions till now? Any questions? Okay, it is fine. So let me repeat the procedure, what we are doing. First of all, the first step, for designing the drill string is to know the collapse loading, collapse pressure. Now, what is the formula to find the collapse pressure is this one. 0.052 multiplied by the mud weight multiplied by the length of the drill string. This is the total uh, formula for finding the collapse rating. We are trying to have the drill string which is 12,000 feet. Okay, now 12,000 feet multiplied by 10 multiplied by 0.052. This 10 is the mud weight of the our drilling fluids that we are talking about. So total will be 6,240 psi. Total rating of this one. Now this 6,240, we have to check the pipe that we are going to use. Has it collapse rating is above it or not? Because we have to use the pipe, its collapse rating should be higher than this one. Now, when we go through the tables, which the table that we used, which is the data collapse rating data table, we said that we have 5-inch drill pipe, outside diameter. Its weight is 19.5. The grade E's collapse rating is 10,000 psi. Now, this 10,000 psi is well higher than 8,890 psi. We added the safety factor, which is 12.5. Now, we selected in the end based on the collapse rating, okay, we are going to use the grade E drill pipe, which has weight of 19.5 pound per feet drill string, pound per feet. And now, based on the table, we find out its internal diameter is 4.276 inch. Okay. So now we know the internal diameter, we know the external diameter, and we know the weight of this one, and we know the collapse rating. This is the step one. Now, as I said that we have to know 2 points here. A tension, we have to make this line, tension load line, and we have to make the compression line. Let's start with the step one, which is the tension line. Now, in order to have the tension line, you must know what is the collapse pressure of the pipe, as we already calculated, which is 6,240 psi at 12,000 feet. Now, what we will do, the other step, in order to have the tension load line at the point of 12,000 feet, uh, we need a collapse pressure and we need the area of the drill pipe. Now, how we find the area? We have the outside diameter, okay, and we have the inside diameter. Let me check. Yes. Okay. The area of, we have to find the area here. Now this area, we are talking about the area of the drill collar, which is 6.25, is already given in there in the data. So here it is 6.25 multiplied by 213 by 14. So this is the outside diameter of the drill collar, and this is the inside diameter of the drill collar, which is 213 by 18. So in order to find the area, we have this formula pi by 4. This is the outer diameter of the drill collar. This is the inside diameter of the drill collar. When we square both of them, we find the area. So the first force that we find out, the formula is pressure multiplied by the area. So we simply calculated based on that one, 6,240 multiplied by 24.47, and we find out the first force that we have applied here. Okay. Now the second thing that we have to find out is the weight. Okay, the weight of this drill collars that we have at 12,000 feet. So what is the weight that we have? Now look at this 20. 20 is the total number of drill collars we are using. The value is given here, 20 drill collars. And each drill collar is 30 feet. We are using the standard range 2, and each length is 30 feet. So what is the weight of the drill collar total? They have multiplied here 20 multiplied by 30, and also this weight per feet of drill collar is given, which is 49,560 pounds is the total weight of the drill collars. Any question? Okay, let me go back and tell you what we are doing here. We are trying to know, look at this table, we are trying to know the F1 force here at this point. Okay, then we will have F2 force at this point. So we will have 4 points. We are trying to know the 4 points: A, B, C, and D. We have to do 4 calculations. For now, we just did the calculation number A, and calculation number A has how much is the force and how much is the weight at this point, at point A. Okay, we are right now trying to know what is the force here and what is the weight here, and we are here. We force is 152,693 pounds, and weight is 20 multiplied by 30 and by multiplied by 2.6. 20 is the number of drill collars, 30 is the length of drill collar, and 82.6 is total weight. Okay, now we are at the point 2, which is the 11,400. We said that the total length of drill collar is total length of drill collar is 20. There are total 20 drill collars, each is 30, so total length is 600 feet. Now this 600 feet, we have to minus it from the 12,000. So now we are at 11,400. Why we are minusing it? Because now first value that we calculated, it was at the bottom, 12,000. Now the second value is here at this point. Now we have to minus whatever is below it, which is 600 feet of drill collars. Okay, so for that, again, we have to find the collapse rating pressure. Okay, 0.052, same mud weight, which is the 10 already given in the data. And now we multiply 11,400, and our now collapse rating is 5,928 psi till 11,400. So we have to use whatever is should be above this one. Now this time, we have two things involved. We are talking about the neutral point. Now at this neutral point, when we are talking about the neutral point here we have to consider the weight of the area of the drill collar also, as well as the area of drill pipe also. So that's why in this calculation we are using the area here. The 6.25 is the outside diameter of the drill collar, and this 5 is the outside diameter of the drill pipe. Then we have the inside diameter of the drill pipe, which is 4.27. And then we have the inside diameter of the drill collar here. To find out, in final conclusion, we find out the total area using the drill pipes and drill collars ID and OD, both of them. And finally, we find out our area, which is the 19.19 inches square. So based on this one, area and the force, we calculated the force, we multiplied the area with the pressure, we find out the force 2 acting on it and the weight 2 acting on this. Now when we talk about this weight 2 here, this is the 11,400 because we are right now working at point B and C. At point B, the total length of the drill string is 11,400, and the length of the per feet weight of the drill pipe is 19.5, which is the nominal weight used at approximation, which is the, you can say now, 222,300 pounds, the total weight of the drill string. Now we have calculated 4 points. We have force 1, we have weight 1, and we have force 2, and we have W2 here. We have 4 points. Now I have to calculate the tension at the bottom, top and bottom of the section. And now, as I said, the compression represents the minus value. Compression represents is the minus value, and the tension we talk about in the positive value, plus value. So when we write it down, this 1,152,693 pounds we have calculated from here. Let me find out where it is. Here it is, the force one that we find out, which was at the bottom based on the 12,000 feet. This was 152,693 was the force one at the bottom. So this 1,152,600 we write it is at the bottom of the collars, because the bottom of the collars, because of the weight of the drill collars, is under compression. That's why we use the negative sign here. We have used it. Then we go at the point B. We are talking, as you see here, we have 4 points here. These 4 points we are talking like this one: A, B, C, and D. The A point is at the bottom of the collar, B and C are at the neutral point, and D at the tension at the surface. So the bottom of the collar, we already calculated the force, which is in tension, which is the minus 152,693 pounds. Now at the top of the collar, we just minus the weight of the section, which is 49,560. We got the tension at this point, which is the 103,133 pounds. This one, we just add this one, the value, the second value that we find out. Then at the bottom of the drill pipes, we just add another one, the value of the drill pipe, which is we calculated the force to here, which is 113,758 pounds here at this point. Here at this point. So now, because it is neutral point, so you see that the impact is minimum, which is 10,625 pounds of the weight, because the weight is adjusted because it's a neutral point at the same point. Now look at the weight and forces at the top of the survey, which is the highest one. So at the top of the drill pipe, here we are talking about, when we talk about top of drill pipe, we are talking about at this point, D, point D. Here the forces are the maximum because we are holding all the drill pipe and drill collars and string, all of it here at this point. So here this 10,625 multiplied by the total weight of the drill pipe we are using. So total weight now is 232,925 pounds. Okay. Then we have to plot all of them points like this point in our chart. Okay. Our chart. So let's look at it how we do that. What we will do here, we will make the graph, which is the showing the forces here at the top, starting from minus 150,000, minus 500,000, plus 0, then all those tension load line we have to make it, along with the depth here. Now, the minus this section below 0 is showing the compression. Here we are talking about the compression. And here we are talking about the tension, the above part. If you look at this chart, we have a line here which is 0. From the, if you go to the left side, we are talking about the compression. If you go to the right side, we are talking about the tension line. Okay, we have number of lines, we'll talk about them, all of them, but let's look at the first one that we are talking about. Okay, the first one, let's look at this one, which we are talking about, the first line, which is the tension load line. This first point here is the same point we have plotted as this one, minus 152,693. This is at, we have plotted at this point. Then the second point we have plotted, which is above 600, and which is 103,133 here. Then the third point we are talking about, which is now we are talking about in above 0 in positive. Okay, this one is about this one, 10,625, just above 0. And the last line which we are talking about at point, of course we are talking about the depths also. Here the depth is 12,000 feet at this point. Here the depth is 11,400. Here the depth is same 11,400. That's why you see we have 2 points at 11,400. This is the 12,000 depth. This is the 11,400. This is the 11,400. And then from 11,400 to the surface, we have the total weight tension load line, which is this one, approximately 232,000. We are talking about the first line that we have made. Okay, any question for now? Any question?
Sir, can you explain how W2, the second weight, was found?
Okay.
So the one before, the slide before.
W2. Okay, let's look at it, what we want to know, what we want here at this point. We have to calculate F1, F2, W1, W2. Okay. F1 is what we are doing. We have collapse pressure and we are multiplying it by the area. This is the F1. Okay. Now, then we have to find out the F2. The formula is same here, collapse pressure multiplied by area, but we are using V minus the length from 12,000 minus 600 is equal to 11,400. Now, question is why I minus 600, right? If anyone can answer, why I minus 600?
Drill collar length.
Yeah, it is the length of the drill collar. If you look at this one, if you look at we minus the length of the drill collar we are talking, because now we are talking about the point B, so we don't need to consider below point B, and below point B we have 600 feet length of drill collar. Okay. Okay. Now we are talking about the weight one. Okay, weight one formula is the, if I write the length of drill collar multiply by the size, total number of drill collars multiply by the length of drill collar multiply by the weight per feet. Okay, we have three values here. Now, as you see in the, from the given example, the total number of drill collars we have used 20. So this is the total number of drill collars. Each drill collar's length is given 30, and each weight per feet of drill collar is 82.6. So this is how we calculate the W1. Okay. Now let's talk about the W2. Now W2 we use the same story. We have the total number of, this time, drill pipes, and we multiplied by the length of the drill pipes, and we have the weight per feet, same story. Now the length of the total drill pipes is 11,400 and total drill string length is 12,000. So 600 is drill collar and 11,400 is drill pipe. So total number of drill pipes are 11,400. Then the length of each drill pipe is also 30 feet. Okay. Yeah. So it's 11,400 is actually given, total length is already given. Okay, which is the multiplication of these two. In this case, these two values, total number of drill pipes and length of drill pipe, both are, if you multiply both of them, is total given is 11,400. So if you ask me like how many drill collars you have used here, so approximately you can say that you divide 11,400 divided by 30, which is, let me calculate.
That's 380.
Yeah, so 380 drill pipes we have. So 380 drill pipes, the length is 30 feet and weight per feet is 19.5. So we get the total weight of drill, all the drill pipe is 222,300. So now we have to create the tension and compression load line. For that, we just have to do the minus plus with all those four values. The first value is in compression at the bottom, and we find out from here force 1, which is 152,693. We write it as a minus here because it is in compression. Then we added the value at the top of the collar. This is the bottom of the collar. If you can see from here, this is the bottom of the collar. This is the top of the collar. This is the bottom of drill pipe at the same time. So if I mention it here, we have 4 points here. We have bottom of drill collar. We have top of drill collar, we have bottom of deep drill pipe, we have top of drill pipe. Let's look at the this first value, bottom of the drill collar, is we are talking at this point. Okay. Then if you ask me the top of the drill collar, we are talking about this point. This is the top of the drill collar. This is the bottom of the drill collar. Then if you ask me the bottom of the drill pipes, as you see that this is the bottom of the drill pipe. Okay. What is the top of the drill pipes? You look at it. This is the top of the drill pipe. So we have four values: bottom of the drill collar, uh, bottom of the top of the drill collar, and if you see that top of drill collar and bottom of drill collar are at the same point, okay, because they meet there. So that's why they are called the neutral point. They are not in compression and they are not in tension at the same time. So based on that, we have the bottom of collar, which is minus 152,693. Then we have top of collars minus 152,693. We add plus 49,560. We have this value. At bottom of drill pipe, we have this value and 4.1. We will use these 4 points to design the drill string in final. Okay. So what we did, we plotted 4 of these points here. This is the bottom value, which is minus 150 something, as you see there here, at 12,000. Then 11,400, we have 2 points. One, the top of the collar and bottom of the drill pipe. So this is the top of the collar, which is 103,000 something, which is, we plotted it here. Then the third point, we have plotted it here, and this is the one, 250,000. Okay, but that's not the end of the story. We have lots of the safety factors that we apply in that case. So the first safety factor, which is the 15%, which is the maximum allowable load. What is the maximum allowable load at the possible load we have? So we find the another value, which is the allowable load that we can use on this drill string. The total safety factor is 15%, so we just reduce that 50% from 100%. Total allowable load given is 395,000. It should be given also. Okay. So this allowable load comes from the size of the rig. How big is the rig? So some of the rigs do not allow that much weight. Yeah, this value 395,000. This is the maximum allowable load for the drill string. This is based on the capacity of the derrick. If derrick is big, then this load can sustain that much load, which is 395,000. So this rating comes from the derrick rating, that how much the derrick can give the load on the drill string. So this is the maximum allowable load. So we also plot this one, 335,750. We have mentioned this one here, which is the maximum allowable load, to the 11,400. 11,400, we have the same value at the weight of the drill pipe. The neutral point is 10,000 something, and from here we put another line, which is 353,000. So this is the maximum allowable limit. So whatever you are doing, it has to be below that, because this is the maximum load derrick can handle. Otherwise, derrick will collapse, your rig will collapse. So whatever drill string you are following, you first calculate the total maximum allowable weight that derrick can handle, and you have to have drill string. Its weight should be less than this one. So what you do, you use less than this one at this point. Okay. Now let's look at the other one. At the surface, we have another safety factor, which is the actual loads that we can obtain. So in actual load, we have to multiply 30% more, because again we are adding the safety factor here at this point. So if you look at the safety factor, 30%, the value that we calculated here was 232,922. This is the top of the drill pipe. This is the total weight that the derrick has to handle. So we have to multiply is by 30% safety factor, and we see that if it is less than maximum allowable limit or not. So we will just multiply that one here. So we multiply 30%. If you multiply 31.3 with 232,925, you get this weight, 302,861. And this was the bottom, 10,625. So this one. So if you add this line here, okay, so your value will be around 302 something at some point. Okay. So now we have two stories going on here. Okay. We have to look at where these 2 points meet. They are meeting around less than 4,000, or you can say nearby 3,000 at some point here, which is the two line, the maximum allowable load, which is 350,000 something above, which is, and this is the load that the drill string has to carry based on the 30% design factor, design load of this one. So what we will do in this one, from 0 to 2000, since there is a chance of collapsing from 0 to 2000, we will use different grid. Okay, now what we did actually here, we have plotted different lines here. We have, you can see 1, 2, 3, 4, and 5 different lines. First line was the one which we found out from this graph, from these values, 4 values. This is the first one here. First one here. The second one is the maximum allowable load. The maximum allowable load is the one which is the allowable load. So what we did, this is coming from the derrick side, the maximum allowable load. Here it is, the maximum allowable load, and safety design factor is 15%. So we just minus that 15% from 100%. So total maximum we can allow is 335,000, which we mention here, 335,000, which is somewhere here between them. Okay. Okay. Now, if you can see that our line here and nearby the 2000 is crossing the maximum allowable load, which is this one. Okay. Then we have the other values, which is one of them is the margin of overpull to obtain the design factor. So in the margin of overpull is the one, what is the margin of overpull? Here's the margin of overpull, is usually above 100,000 pounds above the normal value needed. Okay, this is needed in order to consider the overall drilling condition, hole dragging, getting stuck or something. Okay, slip crushing or dynamic loading. This margin of overpull is needed because of the safety factor. So we have to consider the margin of overpull also here. Whatever the value we get, which is 232,000, 232,925, we added 100,000 with it, and the value is 332,000. Similar value we have added with the bottom of the drill pipes, which is 100,000. So we plotted the same value here. We have same value here, this one. So this is the tension load with 100,000 of margin of overpull line. Then we have the slip crushing factor, which we have to consider. So for example, we are using whatever slips you are using. For example, you are using the slips size, which is 12-inch. Slip is the tool that is used to control or hold the drill string when we are changing or adding the drill pipes. Here it is. So length of the slip is given here, which is the 12-inch. Based on this length of slips here, 12-inch here, and the factor of, we are using the drill string, which is the 5-inch. So based on this 12-inch, which we go and friction of coefficient, and 5-inch, our loading capacity is 1.54. Coefficient of friction Based on this slip factor, we have also multiplied this here, which is the 1.59. So we have also the tension factor, which is 375,351. We also plotted this line here also. So now we have plotted all the 5 points. This one is the original one that we calculated. The last one is the maximum allowable limit, which is 330 something here. And the total capacity that we can allow is 355,000. Then we have the 3 design factors. One of them is the design factor, tension design factor. One of them is the margin of overpull, which is we are adding 100,000 pounds. And then we have the slip correction factor, which is the 1.9. Then based on this chart, once you develop this chart, you see that at the value of 2000, there is a chance of bursting or collapsing of the drill pipe. So what we did here, from the 0 to 2000, we are using the grade E, the heavier pipe, which is 25.6 pound per feet, because its collapse rating is use one. Then from 2000 to 11,400, we are using the 19.5 pound per feet, grade E. Then from 11,400 to 2000, we have already given drill collars, which is 600 feet of drill collars we are using. Okay. In practice, 2 grades of drill pipes are used available on the rig, and you have to design your drill string based on the availability of the warehouse, in your warehouse, whatever you have. So now I will repeat the procedure again to design the drill string, what we are doing actually. So any question before I review what we have done? Any question? Okay, I will go back here and try to discuss what we are doing. See, what is our objective here? Our objective is to design the drill string. Now, this drill string consists of drill pipes and drill collars. Okay, we said that drill collar, function of drill collar is to provide the weight, and function of the drill pipe is to provide the length. Now, when we are talking about, in the question we have to design the 12,000 feet of drill string. Now, in this 12,000 feet of drill string, 20 drill collars are used, and each is 30 feet long. So the total length of drill collar is 600, and the remaining one is 11,400. So if I put this here, from here, this length here, from here to here is 600, and from this point to the surface is 11,400. Okay, 11,400 to 600 will be total will be 12,000. Okay, so total 12,000 is the total length of the drill string. 11,400 are the drill pipe, and lower are the 600 is the drill collar. Now, what is our job? Our job is to find the forces acting on this drill string. And what are the forces we are trying to know is the compression and the tension. So we have now 4 points we want to calculate at the bottom of the drill collars. Then we want to know the forces acting at the top of the drill collar. We also want to know the weight at the bottom of the force at the bottom of the drill pipe, and weight at the top of the drill collar. So we need to find out these 4 values. How we find out these 4 values? We have to look at, first of all, our step 1 is to know the collapse rating. Based on the collapse rating, which is 6,240 psi, okay, we find out using this formula. We go back to the table and we find out that the grade E pipe we can use for the drill string for all the length. Then we discussed that we have to find out the compression and the tension in the drill string. We went further and we did our calculations based on that. The first force we have find out using this one, and the force, the formula to find the force is pressure collapse rating multiplied by the area. So the area which we find out for the at the bottom of the drill collars, it should be minus of the outside diameter of drill collar with the minus of the inside diameter of the drill collar. So the area of the drill collar is 24.47 inches, this one. And this one is given also, outside and inside diameter of drill collars are given here at the same point. Now, once you have the area, you can easily calculate, multiply the collapse rating with the area, you find out the first force area. Then you have to find the weight at the of the drill collar. How much is the total weight of the drill collar? So 20 is the total number of drill collar used. Each section is 30 feet and total weight per feet is 82.6. So this is the total weight of drill collars we have used. Then in the second point, we have 11,400 force 2 that we are trying. Again, we are using the same formula, but now we are using at the bottom of the drill pipe. So that's why we minus the 600, as I mentioned here. We minus the length from 12,000 to 600, it become 11,400. Same value, we find out the collapse rating now at 11,400, which is the 5,928 psi. Also, we found the area. Area is the outside diameter of the drill collar minus the outside diameter of drill pipe. We have mixed areas here, drill pipe and drill collars, because we are dealing with the neutral point at this point. So using the area and the pressure, we find out the force 2 at the bottom of the drill pipes. And then we have found the weight of the total drill pipes we have. So 11,400 is the total length of the drill pipes. And we have 380 drill pipes, multiply by 30, each section is 30 feet. So total weight of the drill pipe is 222,300 nominal weight as used. So based on these four values, we just started from the compression, the first value, we added the second one, then we added the third one, we added the fourth one. By using this one, these four values, we find out. And after using these four values, we have plotted them here at this point, 1, 2, 3, and 4. These four values, we plotted them in this graph. And this graph is the x-axis here is the tension load line in weights, in pounds, and the depth. We are starting at 12,000 feet here. Then we have four different design factors available. So first design factor was the maximum allowable load that we have. Okay, this is by the Derek's load. You can say how much Derek can handle. Then how much slip can handle. Slip crushing factor, we have maximum overburden, margin of overpull. And then we have the actual loads by the design loads that we are using. So we have different design factors. We just multiply design factor with the top weight of this one, 232,925 feet. Then also at the bottom of the drill pipe, which is the 10,625 pounds. We multiply all those design factors with these two values, and then we added them at the chart here. All of them are at the chart. Based on this chart, you can see that now there's a maximum allowable limit was 50,000, but the one of the slip crushing factor is exceeding that limit, reaching to 375,000. So what we did here, because the one of the design factor was exceeding the maximum over limit, so we changed our drill pipe from that point to the better grade of drill pipe. So we are using here 0 to 2000, 25.6 pound per feet grade E, then from 2000 to 11,400 grade E that we selected based on the collapse rating, and drill collars were already selected, which is this size we are already using. So that's all about this question. So any question from this? Okay, this will come in an exam, so just review it on your own after I finish this lecture. And then if you face any problem with this question, please come back to me, because this is an important question in drilling engineering. You will see this in the final exam, in the midterm, or whatever exams we do, you will see all of this example. So just try to give it time, 5, 10 minutes, 15 minutes, as long as when you understand completely, then it is fine. Okay, you have to spend some time on this question on your own. And then whatever questions you generate, come back to me, then we will discuss that. Okay. Okay, now this is the last slide of drill string. This is very interesting. This is talking about the connections, like which drill collar can be used with drill pipe, the combination of drill pipe and drill collar. For example, if you are using the drill pipe 5-inch, what kind of drill collar you can attach with it? Okay, so this is what is mentioned here. For example, here you are using the drill pipe, which is 5-inch. You can use it with the drill collar 8 1/4 to 13/16, but it should be this connection, IC 15.5 and so on. So for For example, here you can see 5-inch pipe to multiply cannot be attached with this kind of the ratio of the tool joints. So you have to look at the tool joints. What are the tool joints you are using? So these are the standard combinations they have made based on the experiences. So when you go on the rig side, these tables should be with you. And if you look at the books of drilling engineering, whatever you are using for your references, they have all these tables. So when you go on the rig side, you have these tables. You should know that which kind of drill pipe should be connected with drill collar, which kind of drill collar should be connected with drill pipe. For hard formation, which kind of pipe you need to use. For soft formation, which kind of pipe you need to use. And how you design the drill string is based on this one. So now in order to design the drill string of these kind of charts, we have softwares also that do this kind of job. That I will share with you in the project. So which software we use. So I will post it today, the project also, as soon as I find time to this one. So any question? Okay, so I leave it for you to relax a little bit, take some coffee, and just review this lecture and this slides, and see whatever questions comes in. Just ask me again, because probably it makes you sleepy for a bit right now. But after you review it, you might have some questions related to that, and we will talk about them again. And remember that you have to solve this example in the midterm or final, if we do it in the assessments here.
So the tables you said we have to bring it ourselves, or would you give it?
Tables, formulas, all will be given.
Okay, all right, thank you.
In my exams, usually I give all the relative informations, formula, tables, conversion, unit conversion, all of that.
Okay, thank you.
Okay. Okay, so that's all for today, and see you in the next lecture then.
Thank you, sir.
Thank you.